Now, in a previous video, I showed you how we are able to calculate the mass of the Earth based on Newton's laws, where our weight, the force of gravity, is equal to the gravitational constant times the mass of ourselves times the mass of the Earth over d squared, which is your distance from the center of the Earth. And we got a pretty darn accurate mass for the Earth. Now, I'm going to show you another way, which involves using the moon. And we've actually used this before. This is how we calculate the mass of the sun, by looking at the orbits of the planets around them. It's also how we manage to calculate the mass of the galaxy, by measuring the orbit, how long it takes for the galaxy to go around. And it comes down to Tycho. No, not Tycho. Kepler. Kepler's third law states that the period of an orbit squared is proportional to the radius cubed. Now, Kepler could only make observations. So he didn't really have the full law, but we have that law. So let's actually make it complete here. So add a few things here. So R is over G, the gravitational constant, times M. M is what we're trying to find, the mass of the Earth in this case. And 4 pi squared. So let's start going here. First, we'd like to fill in the best known values that we have. So for the period of the moon's orbit is approximately 2,361,000 seconds. So that's the amount of time it takes the moon to go around the Earth once. Now, this is something called the sidereal. It's not the same as the amount of time between from one full moon to another. It's actually the time for the moon to go around and come back to where it was in relationship to the stars in the sky, not in relationship to the sun, because it's, the Earth and the moon are both moving around the sun, so that position changes. So it's in relationship to the stars in the sky. And basically, when you get right down to it, it's 27.322 days, and multiply by 24, by 60 again, and you get the number of seconds. So 2.361 times 10 to the 6th, and then again, the whole thing is squared over 4 pi squared. Now, the radius of the moon's orbit is about 384 million meters. So that would be 3.844 times 10 to the 8th meters. And again, that's going to be all cubed. Gravitational constant, I got 6.673 times 10 to the negative 11. And of course, the thing we're trying to find, the mass of the Earth, the mass of the object being orbited. So, going through here, 2.36, 1 squared is 5.574 times 6 times 2 is 10 to the 12th. Okay, still over 4 pi squared. All right, 3.844 squared, or cubed, gives you 56.80 times 8 times 3 is times 10 to the 24th, all over 6.673 times 10 to the minus 11, and of course M, the thing we're trying to find. Okay, basic math, cross multiply. 5.574 times 6.673, and I get 37.20 times 12 plus negative 11 is just 10 to the 1. Okay, 4 pi squared times 56, and you get 2,242. Now, by the way, I'm not really putting it back into scientific notation exactly. It's up to you. You can do it that way. You're not going to get a different answer. I just don't like having to move my decimal points back and forth and back and forth. Every time you move it, there's a chance you're going to make a mistake and move it the wrong way, so I just usually leave that till the end. And so that's why it's still times 2,400, or 2,242 times 10 to the 24. I'm going to move it all when it gets to the end, okay? So, there we go. There's our answer. Oh, I goofed here because I forgot to put something in here. The whole point is to find m. I'm not just multiplying this times this, I'm also multiplying m times that. So m. M is what we're trying to find. Keep going, keep going. Oh my God, get way down here. Okay, so in order to get m all by itself, I gotta divide by 387.2 times 10 to the 1. Divide by 37.2 times 10 to the 1. And what do I get? I get m is equal to 60.28 times 10. 24 minus 1 is to the 23. Let's put that in scientific notation. What do you say? So I'm just going to move that decimal over one place. And 23 becomes 24. And we got the mass of the Earth. Except for, if you watched the earlier video or if you just Googled it, this number ain't exactly accurate, is it? Because if you Google it, you're going to find the mass of the Earth is really 5.972 times 10 to the 24th. Now, what accounts for the difference? Well, the moon is orbiting the Earth, but Newton tells you every action has an equal and opposite reaction. The action is the moon orbiting the Earth. The reaction is actually the Earth being pulled by the moon. If you subtract this, you're going to get a number. I think it's, when I did it, I ended up with something about 5 times 10 to the 22nd. That's the moon. The moon plays a part too. Now, by the way, I worked these numbers over and over and over again, trying to get a better, number for the moon. I just was not able to get it, and one of the reasons why is the moon is very small compared to the Earth. It's less than 2% of the mass. Remember, the moon is formed from the debris left over from when something about the size of Mars crashed into the early Earth. It's really just the debris and the leftovers. So it is very small. And it's just very hard to get that, especially when you're dealing with, gravitation, where we don't have very precise numbers for gravity. And so I just wasn't able to get it, but don't feel bad about it. This is why the first time we ever sent a probe to the moon, we missed. Went off into space there, and also why when we did finally land on the moon, we were surprised to find the moon was far less dense than we had thought it would be. And because it's not always the easiest thing to do to measure these things. But yeah, anyway, it is a correct way to measure the mass of any object going around. Doesn't work so well with the Earth because our moon is so large, almost 2% of the mass of the Earth. But you could use it for Jupiter with its moons because they're about the size of our moon, but Jupiter's much bigger. You can use it for the sun with the planets going around, and it's a very helpful way to do it. You could even use it for entire galaxies. And I just wanted to show you that, and I hope you enjoyed it, and I hope you have a nice afternoon. I will. Bye-bye.